From the city that brought you some of the world's most important discoveries and the Sinclair C5. This is the Cambridge Science Festival podcast.
This is the fourth episode of the Cambridge Science Festival podcast, and I'm Azzy Katiri from The Naked Scientists. In this episode, Ben Valsler goes in search of cracking physics.
Should we open it up and see?
Yeah.
How does it feel?
It feels quite solid, actually. Yeah!
Well done, not a crack in it.
Counting down to engineering mayhem.
5, 4, 3, 2, 1. Whoa! Where's it gone? What is it? It's going down! It's going down! Where has it gone?
And we'll also discover what mathematics can teach us about the spread of chicken disease.
It's something that chickens get, but it's not a disease for them, but it is for us. When we eat meat which is contaminated with it, we get food poisoning.
But first, what can water fleas tell us about the way our body reacts to different chemicals? Well, Sabina Miknovich joins young explorers to find out.
I'm on the Department of Pharmacology stand here in the biology zone, and they've got a stand called Drugs and Daphne. So here with me is Dennis.
We're looking at water fleas, Daphnias, and we're magnifying them using a microscope and projecting them on a big TV screen so we can actually see their tiny hearts beating.
I'm called Sebastian and I'm 8 years old.
Can you tell me a bit about what you were doing over there with the water fleas?
Well, we had these fleas and we were adding different drugs and seeing what they did. Nicotine made the heart pump like really fast, and Coca-Cola made it spin around. And when we added alcohol, we added too much alcohol and it died.
I saw your alcohol one. I think maybe it got a bit drunk and fell asleep. It's probably okay.
Coca-Cola and alcohol can get to the heart pretty fast, and we can really see it changing. We're trying to pick really common drugs and see, does their heart work in the same way as a human heart, for example.
And what have you found?
Well, we found usually caffeine makes the heart beat much faster and stronger, possibly. With alcohol, it does tend to slow down.
Is that the same as humans then?
For caffeine, yes, alcohol is a bit more complex than humans.
So which was your favourite?
Probably adding the nicotine, because I can imagine a little flea smoking.
And what did your smoking flea do? You watched it on the TV screen, didn't you?
It was pumping. The lady said it was pumping so fast, the heart, that you couldn't see it pumping.
But you've learnt a lot then?
Yeah.
And did you enjoy coming to the festival?
Yeah, we went all the way because we live in Kent. My reception teacher told us about it, and so we went, and we liked it, and so we've been going every year since.
Oh wow, so you're a regular fan. You'll be back again next year then?
Yeah.
Great, thank you very much.
Thanks, Sabina. Now, the second Saturday of the festival is always dominated by loads of hands-on physics. Here's Chris, one of the organisers, as he walks Ben Valsler through the day's top events.
Well, I've got a range of things going on today. We're making balloon-powered cars that can also float on water.
I'm making an amphibious car.
An amphibious car? How are you going to power your car?
With a balloon. When all the air comes out, it will push the car along.
Why are you making it amphibious?
So it can go over lots of different types of things.
And what are you doing to make it amphibious?
The water can't get in. It's all plastic.
So it will float?
Yes.
We've also got our old favourite, which is bottle rockets with the Kinder Eggs on parachutes.
It looks to me like you're about to launch your egg, is that right?
Yeah, it is, yeah.
So what have you done to try and stop it from breaking?
Well, we got to sort of make a parachute with the string and everything, and hopefully it won't break.
How do you think it did? I heard it hit the ground.
Yeah, I'm not really sure if it cracked or...
Should we open it up and see?
Yeah.
How does it feel?
It feels quite solid, actually. Yeah!
Well done, not a crack in it.
No.
Do you get to keep the Kinder Egg?
Yeah.
And we have the Cambridge Hands-On Science team in the room next door demonstrating lots of experiments.
Does anyone know what normal nitrogen is? Nitrogen's all around us in the air, okay? And if you cool the air down to minus 200, minus 196, it turns into a liquid like this stuff. It is very, very cold. Why do you think it's bubbling?
It's warming up.
It's warming up. And what's it turning into when it warms up?
Steam.
It's a bit like steam. It's turning into air again. There's liquid air, and when it warms up, it turns into normal air. And so it's boiling. Now, rubber is made up of lots of long molecules, great big long strings of beads. Now, normally, they're all jiggling about because they're warm and they've got lots of energy. So when you stretch it, they can all wriggle past each other and it will stretch. Now, I've made it cold. They've stopped wriggling. And instead of being able to wriggle past each other and stretch, what happens is... So instead of being able to just bend like a normal piece of rubber, it's broken. You can actually feel it's still hard. Okay? So once it warms up, all those molecules start wriggling again. They can bend, move past each other, and they can be flexible again.
Naked Scientist crazy fact number 368. Eyeballs can be used for more than just sight. The northern leopard frog Rana pipiens uses its eyeballs to eat. To swallow food such as a small cricket, it closes its eyes and retracts its eyeballs into its body. These push into the pharynx and against the prey item. Then regular retractions help force the food to the back of the esophagus.
Now, mathematics is very useful, but who would have thought you'd be able to use it to learn about chickens? Here's Chris Smith, who caught up with a couple of researchers who do just that.
My name's Julia Gogg. I'm a lecturer in the Applied Maths department in Cambridge. I'm working on biological problems and using mathematics to try and model them and capture them and make some predictions.
How do you think maths can help us to understand how things like diseases spread around there?
Mathematical models can capture complex systems, so if we're thinking about a disease appearing, you can make a model to represent this and run it and see what happens.
I'm Andrew Conlon. I'm a researcher here in the maths department working for Julia Gogg.
Just tell us what it is you're doing, Andrew.
I'm trying to understand, using mathematics, the spread of Campylobacter, which is a bacteria which colonises chickens. It's something that chickens get, but it's not a disease for them, but it is for us. When we eat meat which is contaminated with it, we get food poisoning. So the models are really about how the chicken itself gets colonised, because only certain types of Campylobacter lead to disease in humans. So what we're trying to understand is, can we make sure that we can keep out the nasty strains from commercial chickens?
This sounds more like a job for a microbiologist than a mathematician, though, Andrew.
Yes, I'm working with the microbiologists to try and tie together the maths and the modelling work with the microbiology experiments that they do. And hopefully, if we can understand the mathematics of how it spread in individual chickens, we can learn something about how it will spread in a flock and in a population, which is something that's a lot more difficult to quantify using experiments and is a lot more expensive to go out and actually test in the field.
Julia, this place is heaving with people. Did you predict as a mathematician it was going to be this popular?
No. Last night when we were setting up our stuff, we had no idea it was going to be like this. This is absolutely brilliant.
Thanks, Chris. Now, the festival provides plenty of activities for school groups to take part in, so we sent Meera Senthilingam to join young engineers rising to the challenge.
I'm going to show you very quickly how you're going to make your rocket. It's really simple. You're going to roll a tube, a piece of masking tape, stick it along the long side of the paper, flick it over, and then you roll it around the tube. Okay, and you want it to be quite a loose fit. You don't want it to stick on the tube. You'll have too much friction between the rocket and the tube and it will slow it down. You want a little tight, narrow cone that's pointy so it can cut through the air.
I've just joined the Meridian School in a rocket building session that's taking place today. They're just in the middle of making their rockets at the moment, and then we're going to go out onto the fens to launch them.
Now, we're going to think about the science behind rockets, and we're going to use this balloon. When I blow up the balloon, the air rushes out of the balloon and goes that way, and the balloon starts to go the opposite way before it whizzes around the room. For every action force, and the action is the air rushing out that way, there's an equal and opposite reaction force that sends the balloon across the opposite way. So two forces Action for the air, reaction for the balloon. When I launch my rocket, all the air inside rushes down towards the ground. It makes an equal and opposite force going up. That's the reaction force.
What's your name?
Clarissa. Ben.
What are you making?
A rocket.
Have you learnt anything new today that you didn't know before?
Yes. I've learnt the name of friction. This is better than the schoolwork.
So do you think things like this will make you enjoy science some more?
Definitely.
Right, so we're out on the fens now, and the groups are about to launch their rockets. It's freezing cold, but I don't think people are noticing because they're too excited about their rockets.
5, 4, 3, 2, 1. Whoa! Where's it gone? Is it? It's going down! It's going down! Where has it gone? Oh, failures!
The first group have just launched their rocket into the air. What's your name?
Matthew.
What happened to your rocket then?
It exploded.
Did you expect it to explode?
No.
When you say exploded, what happened?
All the pieces fallen off it.
But was it still fun?
Oh, yes.
Good. Are you cold?
Oh, yes.
So I'm here with two of the volunteers, Sinead and Ben. So what made you want to help out with this?
I really enjoy passing on my enthusiasm for engineering.
What do you think is beneficial about these workshops in the tasks that they're doing?
Well, anything that can inspire them to become engineers in the future. A lot of them only think of engineering as something your car mechanic does or anything like that, and if we can get them to see all the different aspects of it and they can actually do it themselves and do something that they find interesting and fun, then it might make them think more seriously about a scientific career, which is very important today, especially.
And how do you think the sessions have been going?
Oh, they've been fantastic. The kids have been enjoying it a lot. It's impressive how much they seem to pick up and how enthusiastic they are for a subject they don't really know anything about.
I then spoke to Dr. Joy Ward, who organised the whole event.
I think it's very important that children come to the engineering department and meet the engineers to break down the traditional stereotype of a scientist and engineer, that real engineers are real people who aren't all old and grey, and they can be female as well.
The Cambridge Science Festival, supported by the Wellcome Trust. For more information, go online at cambridgescience.org.
Case file November Sierra 0321. The tragic end of Ken and Wendy Bendy. I caught the case on the radio. A double homicide, and a nasty one at that. I hurried to the scene to find a team of young forensics from Cambridge Regional College. I had to get the lowdown.
We saw a woman with a knife between shoulder blades, and there was a bottle beside her.
She's known to be an alcoholic, but she's obviously been stabbed. I'm not quite sure at this point whether she's also been hit over the head by the bottle, but presumably it would have broken, so that could have been her own. She could have stumbled and someone just came from behind her, because of the footprints at the back indicate that someone entered from that direction, so they just could have creeped up behind her and stabbed her in the back.
The scene inside was no better.
When we came in here, we saw a man that was lying on the floor, and it looked like he had been standing up and fell down, and there were blood patterns on the wall. It looks like he has been hit or shot, or at least something has happened to his head, because we can also see a blood pattern near to his head on the carpet on the floor.
This was a messy case, so I needed answers, and I needed them quickly.
So far, it's hard to tell. We need more evidence. We just started, so we'll see in a couple of minutes.
The forensics team were covering every angle. It was hard to move for photographers, sketch artists, video cameramen, and all in those white plastic bodysuits and impossible to tell apart.
It's important to take photos of the room first, so you have evidence in court.
Right now I'm drawing a sketch of the crime scene, so that we can see what a crime scene looks like and all the proportion and how it looks. And you can recreate the scene.
It could have taken a year or more to sketch the blood spattered across the wall, blood which was now hidden under many lengths of string, each following the longest axis of each spot.
We're trying to make a pattern of the blood, so you can find out where the man was standing when he was killed. We have drawn a line from all the blood spots on the wall, and you can see the pattern is all connected in the end here. You can see the pattern where he was standing, where it was shot.
The pattern was consistent with a single gunshot wound to the head, and while they recorded this, I checked with the forensic team outside.
And now we're supposed to cast the footprint, so we put some frames around it, and we're doing this so we could make out what sort of footprint I think we're going to have.
Right now we're checking for fibers in her clothes with the tape taken from her clothes and then sticking onto a paper.
We're searching the beer bottle for fingerprints by using a brush and some fingerprint powder.
The knife handle, which is very important since the murderer has had a hold of it.
Seems like we've found a great deal of them.
So they sent the fingerprints, the footprints and the fibres, the blood patterns, the bottles and the biological material to the lab. I grabbed the report as soon as it was available. The report came quickly, and some stark conclusions with it. The fingerprints and DNA on the bottles belonged to Wendy Bendy, confirming she had again been drinking. The knife also held Wendy's fingerprints, along with those of her husband, Ken Bendy. One other piece of key evidence tied Ken to the scene of his wife's murder.
We looked at the footprint, and then we saw Ken Bendy's shoes inside, and we could see that his shoes fit with footprints.
Ken must have been driven to murder by his wife's drinking, but he couldn't handle the guilt of his own crime. Only one set of fingerprints was found on the gun. Those of Ken Bendy.
Our own gumshoe detective Ben Valsler, following the trail of a mock murder scene at Anglia Ruskin University. The exercise was designed to teach young students about forensic science. And don't worry, no one was hurt during the making of this programme. That's it for this episode. I hope you have enjoyed listening to these special podcasts, and I hope you can join us next year at the Cambridge Science Festival for more scientific fun and frolics. But in the meantime, a big thank you to all our contributors and to the Naked Scientist team, Ben Valsler, Sabina Miknovic, Mira Senthilingam, Dave Ansell and Anna Lacey, and to the Wellcome Trust for the support. This programme was produced and presented by me, Azik Katiri, and the editor was Chris Smith.